So in a step-down converter without a Snubber circuit, the voltage will look like something like this. No, it will oscillate. But if we add a Snubber circuit, we can control the voltage through the IGBT, so it won't oscillate like that. So now I was talking about the voltage in the IGBT right there. And this here is the Snubber circuit which could control the voltage. When you turn off without a Snubber circuit, the current will look like this. It would take a time so let's say the times here is T off. So if this time is too small, the change of voltage could be too high. So the IGBT has a maximum toleration for how much the voltage can change over time. So let's say that DVCE is the change of voltage in the IGBT, and the time it takes to change that voltage. So let's say that this needs to be lower than 800 volts per microsecond, right? So if T off is 0.3 microseconds, this voltage change per time would be too high. So then we need to add a Snubber circuit, like over here, in order to increase that turn-off time. I forgot to mention that VD here, in this case, is 700 volts. So VD divided by T off would be more than 2000 volts per microsecond. So with a Snubber circuit, we can make the T off become as long as we want. For example, like that. So we can first try to find the capacitance. And in order to find the capacitance, we need to look at the capacitor, the change of voltage in the capacitor over time, because that is going to be equal to the change of voltage in the IGBT, because the RS is now short-circuited. So we could say that DVCE, that is the change of voltage in the IGBT over time, would be equal to C and then IC. So that's the current through the capacitor. Oh, it's divided by. Like that. So, and now we know that this here needs to be lower than this one, right? So we could set it lower than 800 volts per microseconds. And we know that at maximum, IC would be equal to IO, because when the moment before the IGBT turns off, the current, all of the IO current would go here, right? Around the IGBT. So let's say that IO equals to 100, right? Amps. So the capacitance would be equal to IO over DVCE dt, right? Which is equal to 100 amps over 800 volts multiplied by microseconds, right? So this will be equal to 0.125 microfarad. Okay, so that's the constant for the capacitor. Okay, and now we will move over to the resistance, right? So remember that when it's turned on, the current would start flowing this way, right? So we need to find the, okay, so the IGBT has a maximum amount of current that could go through it, right? So when it turns on, the current through the capacitor and the current through the I/O will go through the this IGBT. Oh, it will go here, right? Through the IGBT. So that means that let's say that the Imax in the IGBT is equal to 150 amps. So that would mean that IC plus IO could never be over 100 amps, right? And we could calculate IC because though in the beginning the capacitor will be fully charged up and would be equal to VD because there would go no current through the IGBT and the capacitor, but the um, the current of the capacitor would be equal to the current that flows through the capacitor, which is 0, multiplied by RS plus VD, right? So that means that the VCS would be equal to VD, right? So when it turns on, the IGBT, the voltage over here would be 0. That means that the voltage over the resistance here would be equal to VD, which means that the current flowing through the resistor would be VD, so IR would be VD divided by divided by RS, right? And IR goes through the capacitor or the other way. So this would be equal to IC, right? So we can put this equation that we got for IC into this equation. So that means that VD over RS plus IO needs to be lower than 150 amps. And we know that IO is 100 amps, which means that VD over RS should be smaller than 150 amps minus 100 amps, right? So since all of the variables are positive, we can move RS on the other side, right? So RS equals VD equals 700. So we take 700 volts over 50 amps. Oh, this should not be equal. It should be larger than. And this is equal to 14 ohm. So that means RS should be, oh, I forgot, it's this way. So RS should be higher than 14 ohm. So we could say like RS is equal to 20, just to be on the safe side, right? I forgot to mention one thing, and that is that the capacitance here is maybe too low because we found the limit, the lowest that it could be. So ideally it should be higher. because now the change of voltage per time would be equal to 800 if the capacitance is equal to this. So if it is higher, for example, 0.25, and the change of voltage would be 400, which is more ideal.